We have a few more topics to finish out here in our electrostatics, and the first of those is going to be our electric dipole. So an electric dipole is formed when we have 2 point charges that are equal magnitude but opposite sign, separated by a very small distance. So let's go ahead and draw what this looks like on our 3D space here. So let's say we have this electric dipole oriented on our z-axis, and so what that means is we're going to have some positive point charge on one side of our origin on the z-axis, and equidistant from the origin we can put a second point charge, and we're going to center it on the origin just sort of to make things easier this first time, but we're going to talk about how we can generalize for the case of an electric dipole not centered at the origin and not at our z-axis. So let's say we have q plus, and so not q plus, let's make that positive q, and minus q. So remember, they're the same magnitude, just different in sign. And we're going to define a couple things here. So let's go ahead and define this distance between the two of them as a distance lowercase d. And so let's say ultimately we're interested in finding the electric field and the potential at some point in space p. Well, of course, we can define distance vectors from each of those points to our point P. So we could have, so let's call this to be consistent with the notes. Let's say we have R1 and R2. And so it turns out that if our observation point P is really far away from our dipole, such that that distance is much bigger than the distance separating the two charges d, then really the only position we need is the position vector of point P from the center of the dipole. So I'm actually going to get rid of our negative x-axis here so it doesn't clutter this up. But basically we can just go from, in this case, the origin to our point P, and we're going to call that R. All right? And so we're not going to go through the derivation of all of this, but we're just going to rather just look at some of the key results. But ultimately what we're saying is, for the case of R much greater than D, so we're really far away from that electric dipole, then what we can show, and to see more details on this, you can look on page 151 in the textbook for the derivation, but we can show that the electric potential at that point is given by this P vector dot a unit vector in the R direction divided by 4 pi epsilon naught R squared. All right, so there's our potential, but I've thrown in this new value P. And so it turns out this P, which is a vector quantity, is something called our dipole moment. And so our dipole moment is always going to be directed from negative q to positive q. So directed from our negative q to our positive q. So what that means for our configuration above, our dipole moment is going to be in the positive z direction. So in general, our dipole moment is defined as P is equal to the charge magnitude, and that's of either of the two charges, times a d vector. And the d vector is just the distance between those two oriented from negative to positive. So we could simplify that and say this is q times d, which is just the magnitude of this distance between the two point charges. And then in this case, it's in our z direction. So of course, for different electric dipole orientations, we would have a different dipole moment. And we could also say, well, what if our charges were flipped? So if we had our negative charge on top and our positive charge on the bottom, in that case, our dipole moment would be in the negative z direction. Okay, so with that, we can go ahead and generalize for the case of a dipole centered at some other point. So again, we started at the origin, but let's say we want to generalize for some diode located, so some electric dipole. So generalize for our dipole center at some point located by position vector r prime. And so again, remember our prime notation is going to be for our source points and our unprimed for observation. So if we put it at that point instead of the origin, what we're going to get is the potential at some observation point located by the position vector r unprimed we're going to see that that is equal to, so we're going to have our dipole moment, P, and now instead of dotting that with our unit vector in the r direction, we're kind of going to use the fact that, remember, our unit vector in the r direction is our r vector divided by our r. And so what we do with that is we're going to end up with an r cubed in the denominator, and instead of a unit vector up here, we're going to end up with just that distance between our 2 points, or rather the vector between the 2 points. So that's going to become our r, our observation point, minus our r primed, which is our source point. And in the denominator, we still have our 4 pi epsilon naught. And then we have the magnitude of that distance above in the numerator. And now we're cubing that magnitude. Okay, so this would be our general expression for the potential due to a dipole at any position located by our position vector r primed. So we can also talk about the electric field, because now that we have our potential equation, we can easily find the electric field using the relationship we found in a previous video, which is just E is equal to the negative gradient of our potential. And so in this expression, I'm going to write a form of the potential that comes from the derivation on page 151. So I've not written it explicitly here, but it's a little different form than what I've shown here for our V. But basically what we end up doing is we have a V equation that depends on distance from the point charge r as well as theta. So the theta in this particular case is going to be defined as coming down from our z-axis. To be more general, our theta is defined as coming down from the axis of our dipole. Excuse me. So we're coming down from the dipole axis. And again, so if we were to shift this over to being centered on the origin and on our y-axis, our positive and negative y-axis, then our theta would be defined as coming down from our y-axis. But of course, we don't necessarily even have to align the dipole with an axis. So we would end up getting with a partial with respect to r of that other potential equation, which I've not shown you, but is in part of the derivation, which is qd cosine theta divided by 4 pi epsilon naught r squared, and that's in our r direction, plus 1 over r times the partial with respect to theta. And so I'm just using my general equation for gradient and spherical coordinates. And so that same expression, qd cosine theta divided by 4 pi epsilon naught r squared. And so that is in our theta direction. And so we don't have a phi direction because our partial derivative with respect to phi is 0, because there's no phi dependence in this potential expression. So if we evaluate that, we end up finding that our electric field is equal to P, which is just the magnitude of our dipole moment, divided by 4 pi epsilon naught r cubed times the quantity of 2 cosine theta in our r direction, plus sine theta in our theta direction. And so this is the expression for the electric field due to an electric dipole. And so again, note that theta is going to be the angle between the dipole axis and the position vector. So let's say theta is angle between our dipole axis and our position vector, which is identifying our observation point. So position vector for our arbitrary point P, let's say. And so again, the r is going to just be the distance between those 2 points, and up here the r vector is going to be the position vector for the position vector for our observation point minus the position vector for our dipole. So again, keep in mind that the r and our theta are locally defined. So these aren't our global r and theta from back in chapter 2 when we were looking at coordinate systems. So a couple things that we can look at now is we can look at some differences between our electric monopole versus our electric dipole. So let's say we're going to look at several different charge configurations, and we're just going to kind of tabulate some differences here. So one thing we're going to look at is our variation in our electric field, and also our variation in our potential. So first we can consider a monopole, and so for an electric monopole, all that is a point charge. And so from our previous equation, so way back when we were looking at Coulomb's law, or even from Gauss's law, we looked at the electric monopole or a point charge, and we said that our E is varying as 1 over r squared. Now, if we consider our dipole, we see from this equation that our E is varying as 1 over r cubed, so it's falling off much quicker. So we have 1 over r cubed variation. A similar trend is seen with our potential. So if you remember back to when we were looking at our potential due to a point charge, that varies as 1 over r. And from this general equation for our point charge, well, it's a little bit more difficult to see here because one of these cubes comes from our unit vector expression. So really easier to see from this one, we see that the potential varies as 1 over r squared. So we have 1 over r squared variation. And so this trend actually continues. So if we sort of scale up by multiples of 2, what we're going to get is we get a quadrupole, which would just be 2 dipoles, is going to have an electric field that varies as 1 over r to the 4th, and a potential that varies as 1 over r cubed. And then if we have 2 quadrupoles, we get an octupole. And so the electric field for that is going to vary as 1 over r to the 5th and potential as 1 over r to the 4th. And so of course, if we keep scaling that, it's just going to keep increasing by a factor of 1 over r. So again, just sort of a general trend to notice, nothing that we're going to really deal with too much, but an interesting relationship there. If you want to get some practice with some of these equations, then you can look at example 4.13 on page 153.